Hi students, this is the third lesson for the topic of integration for the International Baccalaureate course, Analysis and Approaches. In this lesson we're going to look at the Fundamental Theorem of Calculus. So in this lesson we're going to be talking about the Riemann integral, or the Riemann sum, which was created by Bernhard Riemann, a German mathematician in the mid-19th century, and it goes like this. Consider the curve y equals f of x between A and B. And you can see how I have split the area up into rectangles, and they all have the same width, delta x. The area under the curve will be approximately equal to the sum of the areas of these rectangles. And to find the area of one of the rectangles, it's going to be f of x, that's the height, times delta x, which is the width. Obviously, the more rectangles, that is, the smaller delta x is, the better the approximation of the area. Hence, if we take the limit as delta x approaches 0, we're going to get the exact value of that area. So the area under the curve between A and B is equal to the limit as delta x approaches 0 of the sum of the areas of all of those rectangles. And remember, the height of one of the rectangles is f of x and the width is delta x. Now this notation is too cumbersome, so we're going to replace it with the integral sign, which means infinite sum, but with one subtle difference. This one has limits on it. So the area is equal to the integral between A and B of f of x dx. Okay, I hope you're still with me. Now we're going to take this rectangle here that's bounded by EMDC and enlarge it. Then we're going to let the area under the curve between A and x be denoted by A of x. That means this shaded area is going to be A of x plus delta x, take away A of x. Now make sure that makes sense to you. So it's everything up to here, take away everything up to here. Now the shaded area, which is here, is greater than the area of the small rectangle here, BLDC. And the area of that small rectangle is f of x times delta x. The shaded area is going to be less than the area of the large rectangle, EMDC, which has area f of x plus delta x times delta x. So we can write this. Now we're going to divide by delta x, and we get this. Now here's the tricky part. We're going to take limits. Taking the limit as delta x approaches 0, f of x and f of x plus delta x are both going to approach f of x. In effect, this is going to squeeze together. As delta x gets closer and closer to 0, that's getting closer to f of x until we actually get equality. So if this side's equal to f of x and this side is equal to f of x, then the limit of this must equal f of x. And so we get the limit as delta x approaches 0 of a of x plus delta x minus a of x all over delta x. And that's going to be equal to f of x. Now this should look familiar to you. This is the definition of the derivative by first principles. So in other words, a dashed of x is going to be equal to f of x, which means a of x is an antiderivative of f of x. So therefore the area under the curve is an antiderivative of f of x. If we want to find the area under a curve, then all we have to do is integrate the function. We've got a little bit to go, and then everything will become much, much clearer. A of x is an antiderivative of f of x. We're going to let capital F of x be the antiderivative of little f of x, where the constant is equal to 0. So we can write a of x is equal to capital F of x plus c. Now remember, a of x is the area under the curve between a and x. And so that means a of a must be equal to 0. There's no area there, it's a straight line. So substituting in a for x, this is 0. F of a, capital F of a, must equal negative c. And so, instead of the c, I'm going to write minus capital F of a. Finally, if x is equal to b and we substitute in b for x, we get a of b is equal to capital F of b take away capital F of a. But this is the area under the curve between a all the way up to b. And we just learnt that that is the integral between a and b of f of x dx. So here's the fundamental theorem of calculus in one line. The integral between a and b of f of x dx is equal to capital F of b take away capital F of a. A and b are the limits of the area, and capital F of x is the antiderivative of f of x with a constant of 0. So the previous two lessons we've been dealing with indefinite integrals. We have an integral of a function dx, but there are no limits on the integral sign. We've just learned about a definite integral. It has limits on the integral sign, and it represents the area under the curve between these limits. Okay, all of that hard stuff is out of the way. Now I'm going to show you how easy this is. Let's look at some examples. We want the integral between 0 and 2 of x cubed minus 3x squared minus 5. So we're going to start by integrating that function. I'm going to put it in square brackets, and I'm going to move these limits over this side. That's just a style. There are many different ways, and if you look online you'll see other ways to write it. Sometimes people will write the limits here. But we've got x to the power of 4 on 4, take 3x cubed on 3, take 5x. In between 0 and 2, and you can see how I didn't put a constant in there. Now we're going to substitute 2 in, take away, substitute 0 in, which of course is 0. And tidying that up, we get 6. Now there's a couple of things to be aware of. The first thing is when one of the limits is 0 with e to the x or cos x. The question we just did, when I substituted the 0 in, it resulted in 0, so I just ignored it. You can't always rely on that because e to the 0 is 1 and cos 0 is also equal to 1. The other thing to be aware of is multiple terms and brackets, and I'll show you an example on that in a sec. So let's look at this example. We've got the integral between 0 and 2 of e to the x dx. When I integrate, I get e to the x, and the limits are 0 and 2. I substitute the 2 in, take away, substitute the 0 in, and we can't discount this. This is 1. So our answer is e squared take away 1. And just a reminder, always leave your answer as an exact value if you can. Example 3, find the integral between 0 and pi of sine x plus e to the x dx. So let's integrate this. We get negative cos x plus e to the x, and our limits are 0 and pi. So let's substitute in pi, take away, substitute in 0. And we need to put that second substitution in brackets. So negative cos pi. Cos pi is negative 1 and cos 0 is 1. So we end up with e to the pi take away 1. Now last lesson we spent quite a bit of time looking at substitution as a method, but all of the examples were with indefinite integrals. We can use substitution with definite integrals, but there's just one extra step. We have to change the limits of integration as well. So let's look at this question. Let's let u equal x squared. Du dx is equal to 2x. So x dx, which is what we want, is equal to du over 2. Here's the extra step. When x is equal to 0, u is equal to 0. When x is equal to 2, u is equal to 4. Let's substitute in and integrate. Substitute the 4 in, take away, substitute the 0 in. And that's it, we're done. There's no need to substitute back to x. Okay, we're going to finish off this lesson with a past exam question. Show that the integral between 2 and k plus 1 of ln of x minus 1 dx is equal to k ln k minus k plus 1. Now recall, when we integrate log functions, we're going to use integration by parts, and we're going to rewrite this as 1 times ln of x minus 1 dx. And we're going to make u equal ln of x minus 1 and v dashed equal 1. So using integration by parts, the subtle difference is going to be we'll have limits here on this first part, this u times v part. We're going to substitute the k plus 1 in, take away, substitute the 2 in. This integral here, I'm going to rewrite the numerator as x minus 1 plus 1 and split those fractions up. So substituting k plus 1 in, we end up with k plus 1 ln k, take away, and putting the 2 in here, we have 2 ln 1, which is 0. And that's going to give us k plus 1 in brackets times ln k, take away, x plus ln x minus 1 with limits 2 and k plus 1. And so we have k plus 1 ln k, take away, and we're going to have k plus 1 plus ln k plus 1 minus 1, which is ln k, take away, and then don't forget your brackets here, put the 2 in, 2 plus ln 1, which of course is 0. Expanding out, k ln k plus ln k, take away 1, take away ln k, plus 2, that's 0, remember. These cancel out, and we end up with k ln k, take away k plus 1. Then we are given that the integral between 2 and k plus 1 of ln x dx is equal to k plus 1 ln k plus 1, take ln 4, take k plus 1. And we're asked to deduce that k to the k is less than k factorial e to the k minus 1 is less than a quarter k plus 1 to the k plus 1 for all k is greater than or equal to 2. So this question is about the area under those two curves and the approximate area that's going to be formed by adding up the areas of these rectangles. So the area under this blue curve, the blue curve is ln x minus 1, is going to be less than the sum of the areas of these rectangles, and that will be less than the area under the green curve, which is ln x. Now I've chosen these rectangles so they all have a width of 1, and so the area of all of those rectangles is going to be 1 times ln 2, and then in this one will be 1 times ln 3, all the way up to, this is k plus 1 here, and this is k. And so this will be 1 times ln k. So now we're ready to set up the inequality. Okay, so this is the area under the curve ln x minus 1. And this is the area under the curve ln x. And this is the sum of all of those rectangles, ln r times 1, from r equals 2 to k. Let's expand that out. So we've got ln 2 plus ln 3 plus dot 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 plus ln k. I can join all of that together. It is ln of k times k minus 1 dot 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 times 3 times 2. That's k factorial. Here I've just joined those two log terms together. So this is ln k factorial. Now I'm going to add k minus 1 to all three parts, like this. Right, let's get rid of these logs. We're going to raise each of those terms as powers of e. So e to the ln k to the k is just k to the k, is less than e to all of that, is less than e to the ln, they will cancel out, so this becomes k plus 1 to the k plus 1 over 4. All right, we're nearly there. Split this up. E to the ln k factorial is k factorial, and that'll be times e to the k minus 1, and we've actually proven it. Okay, that's it for this lesson. In our next lesson, we're going to look at areas and volumes.